Hello everybody. In the previous video, we have discussed about some introduction part of the Laplace transformation. So again, with continuation of this previous video, now let us try to discuss about first and second shifting theorems. So what does this first shifting theorem mean? So first shifting theorem mean, according to our previous knowledge, Laplace transformation of any standard function can be evaluated pretty easily, isn't it? So therefore now Laplace transformation of one can be written and the Laplace transformation of t can be written, Laplace transformation of t square can be written, Laplace transformation of sine at cos at will be written. And by using some linear property also we have solved few Laplace transformations of the given functions. So in that given functions, all those functions are being separated with the addition or subtraction. So we have seen few examples, like some functions are in product also, then we have converted those functions into our required format so that we can apply the Laplace transformation of any standard function formulae. So other than those kind of functions, we have few more functions like e power t into t, okay, e power 2t into sine 3t, okay, otherwise e power minus t into sine square t plus t cube. So like this, few kinds of functions are there. So what we are going to do with this kind of functions? If you observe here, all the functions what we are seeing on the screen, all the functions are having e power t, means exponential term as a common in every term, isn't it? If you exclude this t cube. So whenever we have exponential function in the given function along with some other function in product, then how to find out Laplace transformation? So in that case, to evaluate the Laplace transformation of combination of the functions in product in which the exponential function is there, then we can utilize this first shifting theorem. So therefore, how this first shifting theorem is going to be defined? So as we know that if Laplace transformation of f of t is defined as f bar of s, otherwise capital F of s, as we have discussed, then Laplace transformation of e power at into f of t. You see, two terms are there in product. Out of the two terms, one term is an exponential function. So in this particular situation, we can utilize this first shifting theorem, and whose result is f bar of s minus a. Means, let me tell you in a simple way, that is, let us consider this f of t is equals to some t. Okay, so Laplace transformation of t is 1 by s square according to our knowledge now regarding this Laplace transformation. So if we have extra term with this t as e power t, then how to write? We know that Laplace transformation of t is 1 by s square. So this is nothing but our f bar of s. Okay, and here the output is f bar of s minus a. A is nothing but the coefficient of t here. Okay, here the coefficient of t is 1. So what we are supposed to do is, we need to put s minus 1 instead of s in the above f bar of s, which is nothing but f bar of s minus 1. Got it, everybody? Means like Laplace transformation of e power t into t is f bar of s minus 1. What is this f bar of s minus 1? F bar of s minus 1 is nothing but having s minus 1 in the place of s in the function f bar of s. That is nothing but 1 by s minus 1 whole square. So if you see few examples, what we have written here, you see e power at into t power n. And we know that Laplace transformation of t power n is nothing but n factorial divided by s minus s bar n plus 1. That is Laplace transformation of, we know that Laplace transformation of t power n as n factorial divided by s bar n plus 1. But here actual question is what? Along with this t power n, we are having e power at. Then immediately the same term, this term should be written as how? N factorial divided by, instead of s, we should write s minus a whole bar n plus 1. Okay, so in the same way, if we see the next question, Laplace transformation of e power 8 into sine bt is there. So before that, first let us try to memorize the formula Laplace transformation of sine bt. What is this Laplace transformation of sine bt mean? B by s squared minus b squared. Okay, so along with the sine bt, if we have e power at, then what happens? B divided by s square. Instead of this s square, we should write s minus a, and remaining terms are all same. So therefore, Laplace transformation of e power at into sine bt has become b divided by s minus a whole square plus b square. Okay, so therefore next one you see e power at into cos bt. To write this Laplace transformation of e power at into cos bt, we should have a knowledge about what is Laplace transformation of cos bt, which is nothing but s by s square plus b square. Okay, so therefore here we are having e power 18, no? So instead of s, what we are supposed to write s minus a. So the same term should be written as s minus a divided by s minus a whole square plus b square. Okay. Next is sin hbt. So like this, we can derive Laplace transformation of e power 18 into any other term f of t. Okay. So let us see a few examples here. As we have written, Laplace transformation of cos bt is s by s square plus b square. Already we have discussed. So right, so Laplace transformation of e power 18 into cos bt will become s minus a divided by s minus a whole square plus b square. Fine. So this is about first shifting theorem. So after learning about this, what we can say when this first shifting theorem will be utilized? First shifting theorem will be utilized only when the given function possess exponential function in it. Okay, like this. If two functions are in product, one of the functions should be compulsorily exponential function. Then immediately what we can do here, we should write a Laplace transformation of t square, 2 factorial divided by s cube. But instead of s, we should write s minus 1 whole cube. Similarly, Laplace transformation of e power minus t into cos bt, which is equals to s plus 1. Why? Because here we have minus 1. So s plus 1 divided by s plus 1 whole square plus b square. Okay. So similarly, Laplace transformation of 2t square plus e power t into t. Then how to evaluate this? This can be done first by using linear property, that is 2 into Laplace transformation of t square plus Laplace transformation of e power t into t. Okay, so which implies 2 into 2 divided by s cubed plus, here it is 1 by s minus 1 whole square. Okay, so like this, by using the previous knowledge also, by accumulating all the formulae and definition parts from the beginning of the Laplace transformations, we should be keep on applying the suitable formulae for evaluating the given Laplace transform of the function, given function. Okay, so in the same process, what we can understand is Laplace transformation of sin t into cos t plus t into e power 2t. How to evaluate this? So individually we know how to evaluate this. Individually we know how to evaluate this. The same logics will be utilized here. First we need to go with the Laplace linear property, Laplace transformation of linear property. So according to that, we need to separate Laplace operator for both the terms existing in the given function. Yes, we have separated here Laplace transformation of t into e power 2t. Okay, so therefore Laplace here, what we are supposed to do, we need to multiply and divide it by 2. So 2 into sin t cos t plus Laplace transformation of t into e power 2t. Directly we have a formula here. That is nothing but first shifting theorem. We can utilize here first shifting theorem. So here 1 by 2 into Laplace transformation of, according to our previous knowledge of trigonometry, 2 sin t cos t can be written as sin 2t. Okay, plus Laplace transformation of t into e power 2t. So now the functions are being ready for application of formulae. So therefore 1 by 2 into this can be written as 2 divided by s square plus 4. And this is written as 2 divided by s minus 2 whole. Only t no. So only t means 1 by s square. Laplace transform of t square. T. Laplace transform of t is 1 by s square. So what we can write is 1 by s minus 2 whole square. Here we can cancel 2, 2. So therefore the final output will be 1 divided by s square plus 4 plus 1 by s minus 2 whole square. So like this we can calculate Laplace transformation of the given functions by accumulating all the formula from the beginning. Okay, so hereafter let us move on. For after learning about the application of the first shifting theorem in the evaluation of the Laplace transformation of the given questions, now let us move on for the second shifting theorem. What does this second shifting theorem mean? Second shifting theorem mean Laplace transformation of two functions. Here again two functions are in product. And the terms inside the functions are defined in the same way like t minus a. But the two functions are different. One is h and another is f. So then how to evaluate this? So Laplace transformation of h of t minus a and f of t minus a is defined as e power minus a into f, capital F of s, which can also be considered as f bar of s. Okay. So now what we can write the definition? Definition: Laplace transformation of h of t minus a into f of t minus a is nothing but e power minus as into f bar of s. What does this f bar of s mean? F bar of s is nothing but Laplace transformation of f of t. If Laplace transformation of f of t is equals to f bar of s, then second shifting theorem is defined as like this. Okay, so by using the definition we can derive this output. That is, you see, Laplace transformation of any function is given here. Fine. So according to definition, it is written as integration over 0 to infinity e power minus st into the entire function for which we are applying the Laplace transformation. Hereafter, this limitation will be changed from a to infinity e power minus st into f of t minus a dt. Okay, so means when we apply these limitations for the h of t minus a, they will be changed as a to infinity. So after that, integration over 0 to infinity e power minus s into a plus w into f of w dw. So integration have been changed. How? By considering t minus a. This t minus a is there. No, by considering this t minus a as w, this integration have been converted to this. So therefore, by putting all the substitutions, e power minus as will be the constant. So let us keep it outside. The remaining is only e power minus sw into f of w dw, which is nothing but, according to definition, capital F of s. So therefore, finally, what we have derived, Laplace transformation of h of t minus a into f of t minus a is nothing but e power minus as into f bar of s. Right? This is the second shifting theorem formula and derivation. So hereafter, let us see few applications of the second shifting theorem. So what are the applications of second shifting theorem? First example, you see. Here, Laplace transformation of two functions should be there actually. Those two functions are here, p minus 4 whole cube into e power 4, e power 3 into p minus 4. Okay. So therefore now, according to definition, what we can do is Laplace transformation of product of two terms where the terms, where the variables in the two functions should be same. Like this, p minus 4 whole cube and e power 3 into p minus 4 is there. So product of these two terms means here the function is considered as p minus 4 whole cube into e cube into p minus 4. So Laplace transformation of this we are supposed to find, which is nothing but e power minus as, okay, into f bar of s. What does f bar of s mean? So Laplace transformation of this, that is what it is, like e power 3 into t, that is e power minus p minus 3 whole power 4. Okay, so like this, the second shifting theorem will be applied. Right? So in this video, what we have learned is, if we see first shifting theorem, we have learned, which is nothing but this first shifting theorem will be utilized when Laplace transformation of two functions are in product. Then we can utilize this. And second shifting theorem also we have learned, when the second shifting theorem will be utilized means again the two terms in the given function will be in product, but the variables in the two functions will be of the same kind, like t minus 1, t minus 2, otherwise t minus 3, t minus 3. So the only basic important point we need to check with the question when this first shifting theorem should be utilized and when second shifting theorem will be utilized. When we have any exponential term in the given function, okay, when we have any exponential function in the given function, immediately we should go with the first shifting theorem. Otherwise, we should go with the means we need to check whether the variables in the two functions in product are in same kind, like t minus 1, t minus 2. If they are, then we should go with the second shifting theorem. So these are the few applications and definition part of the first and second shifting theorem, and we'll meet again in the next video.